Now, so previous one we have seen the first order low pass filter. Now, this is our second order high pass filter, right. Why this is called second order? When we see we have two combination of R and C capacitors, two combination of R and C pairs, right. So, one, if I have one combination of C and R, it is called first order high pass filter. If I have two combinations, this is called second order high pass filter. Now, because we have two capacitors and two resistors, the cutoff frequency will be calculated as 1 by 2 pi into root of R3, R4 and C1, C2, right. Just recall our high pass filtering sessions, you can easily understand that. And since this is connected to the positive terminal, the input is connected to the positive terminal of an operational amplifier, this is a non-inverting type, right. Since it is a non-inverting type high pass filter, so high pass filter, the gain of the system is nothing but 1 plus R2 by R1. So, the resistors that we use, the values of resistors R2 and R1 that we choose decides the complete gain of the system, right. So, in this case we require to design a cutoff frequency somewhere around close to either 0.5 hertz or 1 hertz, right. So, in this case we have chosen a resistors values as well as a capacitance value, so that when we calculate cutoff frequency we got a value as 1 hertz. But how do we calculate? The cutoff frequency is 1 by sorry, there is a wrong in the formula, it is nothing but 1 by 2 pi into root of R3, R4 and C1, C2. So, in this case we have chosen R1 and R2 as 1 kilo and 1 kilo. So, when you observe, this is a 1 kilo ohm, this is 1 kilo ohm. So, when we calculate a gain is nothing but 1 plus 1 k by 1 k, which is nothing but 2. So, if I apply 1 volt, I will get an output as 2 volts. If I apply 0.5, I will get an output as 1 volt, right. Apart from using our instrumentation amplifier, some amount of gain can also be given, can also be applied by using these operational amplifiers too, right. Then we have chosen R3 and R4 resistance as 1.5. So, this is 1.5 k and this is also 1.5 k, right. And what about C1, C2? So, both C1, C2 we have used 100 microfarad and this is also 100 microfarad. So, when I calculate FC is nothing but 1 by 2 pi into root 1.5 k square into 100 micro square, right, because R3 is equal to R4 in this case as well as C1 is equal to C2. So, C1 C2 I can write it as C1 square, R3 R4 I can write it as R3 square. So, 1.5 k whole square and 100 micro square. So, when we calculate, the value will be almost equal to 1 hertz, the value we got is 1.06 hertz. So, which is equal to 1 hertz, right. Now, how do we understand? So, similar to that of our low pass filtering circuit, even in this case what we do is that we will connect this particular circuit, we will do the circuit design in circuit design simulation software. We are using multisim, we will go with a multisim, we will use the same resistance values and capacitance values. Since this is a cutoff frequency of 1 hertz, we will go from somewhere around 10 millihertz to some greater than 100 hertz, somewhere around 200 hertz also we can go, right. We will slowly increase from this frequency to this frequency and we will use an input signal of 1 volt. Now, since the gain is 2, we will get an output as 2 volts, that we can observe, and as long as the output is 70.7% of my input. So, since we are using the output is of 2 volts, so that means 1.414. As long as the input is lower than 1.414, that means the signal is completely attenuated, that is the 3 dB line. So, when the input is higher than 1.414, that means the signal is being passed, that is greater than our 3 dB line. So, that point wherever it is almost equal to 1.414 volts, I can say this is our cutoff frequency, right. This is the cutoff frequency of our high pass filter. Now, we will go to our simulation. I will create one more circuit. So, I will save this circuit as high pass filter, save, name I will write it down as high pass filter, and the cutoff frequency we are using is 1 Hz in this case. So, 1 Hz. Okay. So, what we need? We need to use operational amplifier. I am taking operational amplifier, and we are using 2 capacitors and 2 resistance. And what resistance value we have considered? When you see R1 and R2, R1 and R2 we defined here as feedback and the normal resistance, right. This is R1 and this is R2. So, I will use the same resistance value as well as same R1 the notations too. So, R1 I am keeping it here and rotating it, and I am also taking R2, this is R2, R1 and R2 are same resistance value. So, I do not have to change the resistance, I will be connecting it here, negative feedback, right. So, the gain, the input resistance and the gain resistance, the feedback resistance which decides the gain of an op amp is done. Now, what else? We have to do the filtering part, which is nothing but C1 R4 is one part, C2 R3 is another part. So, I will take 2 resistors again. So, one is R3, this is our R3 resistance, and the value that we choose is 1.5 K, change it to 1.5. Sorry, this should be 1.5 K, right. Then we will choose one more resistor as a feedback, which is a positive 1.5 K at this point, and this terminal should be connected at this point, and this should be connected at the positive terminal. Now, what about the other one? Other one has to connect it to ground. Then what else? I have to take capacitance. So, I will go with 2 capacitance, one is C1 and other one is C2. So, the value of capacitance that we use is 100 microfarad, 100 micro, even here 100 microfarad. Now, let me make a connections here. So, this particular point has to be connected here and this point has to be connected here, right. So, with this combination of a circuit we can observe high pass filtering at a frequency, at a cutoff frequency of 1 Hz. So, in order to observe that signal, so we have to connect the input source. So, I will take an AC voltage, I will connect it here and this is grounded. So, one terminal one probe I will be connecting at the input. So, both the input and output I can visualize, other one is at output side. So, this is nothing but our green color represents the input signal and the blue color represents output. So, to visualize in a frequency domain, I will change the settings from interactive to AC sweep. So, what do you mean by AC sweep? AC sweep is an internal function. What it does is that rather than you keep on changing your input frequencies at particular frequencies, the system has already pre-programmed such a way that the input signal frequency will start from 1 Hz to the minimum frequency that you set to the maximum frequency that you set with an intervals of some default parameter, default values. It will keep on increasing the values and you can observe the output voltage at this particular point, right. So, I will go to the grapher, let me run it, we can see the signal now. So, since you also have a phase, I do not want to look into the phase. So, I will remove both the phases. Now, here we can see input is green, right, and output is this one, is not it. Now, what I need? The input frequency and this frequency. So, this I will make it as 200, whereas this I will make it as somewhere around 0.01 Hz. So, in this case for the sweep configuration, I have changed some setting parameters. We changed the start frequency as 0.1 Hz and the stop frequency as 1000 Hz here, and the points per decade is 10. So, only thing what we have to do is that once we select the sweep, we have to go to the settings. From the settings here we have to change the parameters to 0.1, 1000 Hz and how many points per decade we require. Once it is done, when we start simulation, it starts simulating it. So, in this case even if you observe the input is green and output is blue. So, what I will do is that I will change, since I may not require both the phases, I will remove both the phases. I have both the magnitudes. I am making cursors temporarily off right now. So, observe carefully here, the green indicates our input signal and the blue indicates our output signal, right. Now, so this is a logarithmic scale, the magnitude is completely logarithmic. Here we can see the magnitude is completely logarithmic and the green is at 1 dB, 1 magnitude. But what about the blue? Why it is in 2 dB? If you remember correctly, the gain of an op amp is 2. So, that is the reason the output is having double than that of the output magnitude is double than that of the input magnitude. Now, what about at different frequencies? When you see, no matter what, at what frequency you are at, the input is always having an magnitude of 1, but whereas the output depends upon the frequency, it is slowly increasing and one particular point it has become 2 dB. Now, if I want to calculate the cutoff frequency of this particular filter, right, the characteristics, if I see, it looks like our high pass filter characteristics. So, whatever we design is also high pass filter, 1 Hz cutoff frequency. Now, if I want to visualize, what I will do is that I will take a cursor, I will go with an amplitude cursor, y axis cursor, and I will put C1 at 1.7, right, because the 3 dB line is nothing but 3 dB to our maximum amplitude. Maximum amplitude is 2. So, 2 minus 3 dB. So, the magnitude should be 2 minus 0.3, it should be somewhere around 1.7, right. So, I will keep somewhere around close to 1.7 value, 1 minus 1 sorry, this is C1 1.8 sorry. So, I will be keeping close to 1.7, that is our 3 dB, magnitude of minus 3. So, here this point is nothing but R. So, when I observe it, three magnitudes, when you observe that this is very close to the 1 Hz, right, or one way to look into that is, rather than going into this, we can go to interactive and we will split it. Let me close this, we will split it, we will change the frequency from 0.1 Hz itself, right. Let me run it. So, we will change the settings to right. So, what is happening now? The peak voltage that we get is nothing but 2 volts, right, as we know that. So, in order to understand that, what I will do is that rather than going with a low high value, we will go from lower value. So, make it as 100 Hz. Now, go to the settings. So, we can see 2 volts to 2 volts. I will increase, I will decrease the time division, so that we can see the signal. From here it is clearly observed that the input is green color, output is blue in color, the peak to peak value is 2 volts the input signal, whereas output peak to peak is 4 volts. Since it is a 4 volts, right, why this is 4 volts? Because of the gain as 2, the gain here is 2, and moreover, since it is a non-inverting type of input, we cannot see any change in the phase shift, it is always following the input, right, that we can clearly observe. Now, to understand that, we will create a cursor. So, cursor should be put at, so I will take y axis cursor, the amplitude cursor, and this should be placed at 1.414 volts. So, I will be moving this cursor, we will move the cursor, okay, y axis cursor to 1.414. If you observe here, this is at 1.6, slowly to 1.41 to 1.41 to approximately 1.41. So, whenever the input voltage. So, what I will do right now I am at 100 hertz, I will slowly decrease from 100 hertz to 10 millihertz. So, at what point, at what frequency the input is equal to this C1 threshold is nothing but my cutoff frequency. So, what I will do, I will decrease slowly with a factor of 20. So, go with 80, I am going with 80. So, I will make it as auto, right. So, automatically it will change it, then I will go with the 800 it has gone, go to 60, we can see still it is at 2, 40 still the same, 20 still the same. So, since we have to observe even at a smaller values, smaller frequency, I will increase the time division. So, easy to visualize, then change the frequency slowly from here to 10, same, then slowly decrease 9.5, 7, 6, 5, 4, slowly decreasing it. Now, if you carefully observe, when we observe our characteristics, whenever it is coming close to the cutoff frequency, the input amplitude is little higher, even here we can observe at this point, right. The gain should be 2, but slightly there is a higher gain at the frequency close to the cutoff frequency value, right, that we have seen. This is because of our Butterworth filter, it is a second order high pass Butterworth filter, is not it. So, when we remember or recall our Butterworth filter characteristics, the gain will be slightly increased near the cutoff frequency, right. So, the same thing we can even observe here too, slowly decrease again. See, whenever it is 1 hertz, started decreasing it, 500 millihertz, it is even lower than that of our C1. So, that means the value is somewhere between 1 hertz to 500 millihertz. So, in order to understand, what I will do is that here I will slowly increase to 600 milli, observe the value, no, then 0.7 hertz, 700 milli, not even close, go to 0.8, 705, sorry, 0.8 millihertz, coming close to that value, I will go with the 0.9, right. So, the cutoff frequency is somewhere around 0.8 to 0.9. Now, I will decrease little bit, 895, 870, 865, right. When I see somewhere around 825 to 830 millihertz is the cutoff frequency of this particular filter, right. So, this is the cutoff frequency, but theoretically we got somewhere around 1.06. So, because of the second order filter and that too it is a Butterworth filter, but when we do the experiment we got somewhere around 830 milli, right. Now, we will also look into, so I hope this is clear right now with the simulation. What we do is that we will look into the board, we have already done the same circuitry using our breadboard. So, we use the other part of the TL082. So, previously we have seen low pass filter, now we will see the high pass filter on the same op amp just next to that, but we are using the first side of an op amp in this case. Now, when we look into our TA board here, so this part is completely high pass filter circuit. So, this part is high pass filter, this side of an op amp, this side is high pass filter circuit, this is a low pass filter circuit. If we can see two capacitors here as well as different resistors, 4 resistance, 1, 2, 3 and one more here, 4. So, 2 resistors are for gain and 2 resistors are for the filtering thing, and the input is nothing but the input should be given to the C1 and the output should be taken from op amp output. So, even in this case what we do is that, so the board is right now switched on. So, now we will replace input from this from here to the input side of capacitor. So, this is the input side of capacitor, we have connected it to the capacitor, right, and output is 1, and this blue wire we will connect it to the same point. So, we can see the input signal, input frequency in oscilloscope, and output connecting it to the first one. The first one is here. Now, when we look into the output, so right now the frequency that we have given as an input to the op amp is 100 hertz is the input frequency that we have given to this, then this is the output we got. So, I will put both the things to the same point, so easy to understand, right, and even this to little up to the 0 0 position. So, both are right now at 0 0 position. Now, the scale if I observe, this scale is at 1 volt, whereas this scale is at 2 volts. What I have to do is that I will increase, I will put both scales at the same level. So, that means one box even for the input as a first channel as well as the second channel is one box equal to 1 volt. Now, if I observe that, right, here we can see 1 volt and 1 volt. So, what we can understand, so we can see yellow is nothing but our input and blue is nothing but our output. So, what we can understand from the output, we can see that the input and output are following each other. That means that there is no phase shift between your input and output. That is because of we are using second order high pass Butterworth filter, right. The input is connected to the positive terminal, and because of that, because of the input is connected to the non-inverting configuration, we do not see any phase shift. Other one is the gain. Since R1 and R2 resistor that we choose of same value, the gain is 1 plus R1 by R2, which is nothing but R2 by R1, which is nothing but 2. So, we can see the amplitude change of double the amplitude of that of your input. Now, what we have to observe, we have to find out the cutoff frequency. See, in order to observe our cutoff frequency, what I do is that I will create a cursor at a point of 1.414, right. So, 707 into 2, so 1.414, because we have to create a 3 dB line for our output voltage. Output magnitude is 2, right. For 1 volt it is 0.707, for 2 volts it is 1.414. So, I will go with a cursor, I will go as type amplitude, right, and let me put the cursor to 1.414. So, if I observe here, this is right now at 1.4. So, I will try to see whether it is possible to change it to 1.41. Unfortunately, it is not. So, what I will do is that I will fix it at 1.4. I will slowly decrease. Right now, the frequency is at 100 hertz, right. So, I will slowly decrease at a units of 20 hertz till we are at 20 hertz. After that, we will decrease to 10 hertz, then from 10 hertz slowly one by one will increase till we see the frequency at what frequency the input voltage is lower than that cutoff point that we set. So, I will set it to 80 right now. What I will do is that go to frequency point and make it as 80 hertz. Any change in the output when you look into the oscilloscope, right, there is no change in the output. Then I will go to 60, even now no change in the output, 40, even same, right, even the same, decreases to 20, same, 10, same. Now, I will slowly decrease 9, but in a simulation we have observed that when the input frequency is getting close to 1 hertz, we have also observed the output voltage is increased. We will also see whether practically it is that we can visualize or not, right. 7, 6, 5, 4, 3, yes, observe. Still at S2, okay, we are going to 2 hertz now, yes. Here if I observe, so what I will do is that I will go to measure, I will create channel 2 peak to peak value. So, from the peak to peak value we can easily understand sorry, this is unable to measure, but that is fine. But we can see that the output value, the blue color one, is slightly higher than this second box, right. So, that means, right, we can see here it is slightly higher than this second box, that means the gain is increasing. Now, I am coming to 1. Now, when it comes to 1, here we can observe that. So, I will decrease the scale, right. From when we look in, when we zoom the input signal towards the CRO, here we can observe that the output is very close to that the cursor, right, but still it is higher, right, it is very close to the cursor. This cursor point is 1.4, right. So, when you look into the cursor, oh, it has been changed, it should be 1.4, right. Right. So, it is very close to the cursor value. Now, I will slowly increase, let me see what will be the change. 1.4 hertz right now, 1.5. Now, when it is at 1.5 hertz, the gain, when you zoom into that, the gain is higher than 2, right. That is what even we have observed in our simulation too. Increase 6, even higher, right, 7 higher, and 8 even higher. So, what I will do is that I will slowly decrease value. Now, we will observe at what frequency. Right now it is 1.3, right now I am setting at 1.1. So, even at 1.1 hertz, the input value is higher than the cutoff what do you call that, the cutoff value, which cursor point, which is at 1.4. Slowly I will decrease to 1 hertz. Now, suddenly it has moved to 1.4 volts 3 dB line. Now, I will slowly decrease, we can see the output is below that cutoff, right. When I zoom into the oscilloscope, we can observe that the output is below the cutoff, which means that 1 hertz theoretically, when I see theoretically we have seen that it is at 1 hertz, even if the practical we can observe that it is at 1 hertz itself, right. But when I slowly decrease it, it is going below that cutoff value, even if I go even beyond lower value below that. So, that means one thing we can clear that for a high pass filter, below the cutoff frequency, the phase the amplitude will be attenuating, it will not be completely removed, but amplitude will be attenuated from the cutoff frequency. And here we can clearly, one more thing we can understand, that since it is second order filter, we can see the drastic change from 1 hertz to when we are decreasing from 1 hertz, right. So, I hope this is clear about our high pass filtering, and the high pass filter is also working as per our expectations, right. Now, we will stop at this point, we will see other filters in the next module. Thank you.